Okay, so we're going to do problem 13.46, section 13.3. This is page 475. A little different approach, putting the writing up first, see if this is easier or makes things more difficult for you guys. So we're going to, question states, do waiters or waitresses earn larger tips? To answer this question, they undertook a study. They looked at 50 restaurants during a 1-week period and randomly selected one waiter and one waitress from each, and what conclusions can be drawn. So the question is really asking, is there any difference in the tips earned between waiters and waitresses? So I'm going to designate population 1 as waiters, population 2 waitresses. From the appendix A, define the sample data. We find that the mean sample difference, or sample mean difference, is negative 1.16. In other words, waiters earn on average $1.16 less than waitresses. Sample standard deviation is 2.22. And it looks like we had, as I said earlier, 50 waiters and waitresses to talk to. And there, again, this is a dependent sample, to clarify that, because we're looking at each restaurant. And each restaurant we can think of as designating as matched pair, one waiter and one waitress from a given restaurant. We're asked to use a 5% significance level, and so with all this information, we can go through the hypothesis steps. First, assumptions, unbiased samples. Again, we just have to take down faith. Second assumption we need is the population distribution of the variable is somewhat normal. Again, you can look at the histogram of the sample data for that. We're not going to do that here, but you want this sample histogram to have somewhat of a bell shape to it. So step 1. Step 2 is our assumptions. Again, this is where we read the question and figure out what we're trying to determine. Our null is going to be, again, the population parameter equals some value. So the parameter here is that population mean difference between the tips earned by waiters and waitresses, equals, and we're going to use 0 as the value there because we're not told to check for specific value. We're just asked to find out if there's any difference between those population means. The alternative hypothesis, again, same parameter, same number, and we're not specifying greater than or less than, so we'll just designate that as not equal to. So that implies with this information we know that the hypothesized difference is 0, and we're doing a two-tailed test because this operator there is not equal to. Okay, so that's step 2 for the hypotheses. Step 3, look at the rejection region. Again, pieces of information that we need. Type of test, two-tailed test. The significance level is 0.05. We're also going to need the degrees of freedom. Remember, for this type of question, it's just the sample size minus 1, which is 49. We're going to round up to 50 since that's our table does not have 49. And this is a diagram of the rejection region. So again, we have rejection region, both tails of distribution. Those boundary points are our critical values. We have 5% total significance level, so we're going to split that 5% evenly between the two tails, 2.5% each tail. And so our goal is going to be to find what are these values, critical values A and B. Okay, so we're going to try to find this critical value, and we can find either value, but we're going to start with the critical value B here because it's in the right tail, and we know our t-distribution table has right tail probabilities. And so at critical value B, the t statistic is going to have a 0.025 right tail probability, 50 degrees of freedom we talked about a couple seconds ago. And if we look at our table, that value is 2.009. Okay, and so that means that our critical value then, go back over here, is 2.009. Critical value A, we can't look up directly, but we know that due to the symmetry of the distribution, that'll be just the negative value, so negative 2.009. Okay, and so what does that mean? Take away to the rejection region, so when the absolute value of the test statistic is greater than 2.009. It's either less than negative 2.09 or greater than positive 2.009 in actual values. Okay. So that ends step 3, the rejection region. Step 4, the test statistic. Don't have the formula here, but it's again the sample mean minus the hypothesized difference divided by the sample standard deviation, which is that then divided by the square root of the sample size. Okay, so we said earlier, sample mean difference is negative 1.16, 2.22 is the sample standard deviation, 50 is the sample size. Plug those values, we get a test statistic of negative 3.694. That is definitely in the rejection region. That absolute value is positive 3.694. So we're in the rejection region, therefore we're going to reject the null hypothesis. Okay. And our final step, quantitative step at least, is to determine the p-value. So what I'm going to do is plug in the test statistic values, 3.694. I need to put both the positive and negative version of those values because it's a two-tailed test. And the p-value is the probability I'll be in this tail or in that tail. So p-value, if I want to write out terms, is probability that I'll be less than negative 3.694, t-statistic with 50 degrees of freedom. Or the probability with that t-statistic with 50 degrees of freedom will be greater than 3.694. Well, we know we can't find that from our table because it's a left tail distribution or left tail probability. But I know that through symmetry these two are equal. So let's rewrite that as 2 times that right tail probability. If we look in the table, we find that for 50 degrees of freedom, 3.694 is beyond the edge of the table. We know the smallest value in terms of subscript is 0.05, and so I know that probability is less than 0.05. Final step is to multiply by 2 to find the p-value. 2 times 0.05 is 0.010, and so the p-value then is less than 0.010. And that concludes 3.46.